we are again in the PLC Professor's Workshop Development Lab, and this presentation is on near the top of the list for the most boring of subjects, at least for me. Now, I probably shouldn't say that, but I find it hard to make math instructions interesting. Typically, with the newer platforms, I tend to use structured text for math. In other words, I will create a separate routine or separate program just for the math for a particular application because I find it easier to express my calculation as an algebraic expression with parentheses and the math operators than with math instructions. However, regardless of what you might use when you're writing programs, you won't get by in this business without troubleshooting other people's programs. And I'm not against using, the math instructions at all, because I do use them. I typically use add and subtract instead of count up and count down. In other words, I take a value, I add 1 to it and store it in itself. In other words, I'll take source A plus 1 and then the result I put in source A. So in other words, every time that instruction increments, I'm incrementing it by 1. I'm adding 1. I'm not adding just 2 variables of various data types. I'm using it as a counter. And the reason I started doing that was because there are certain conditions where a counter instruction, when you're going from program mode to run mode or booting up, that it can, if the conditions are just right, it will increment by 1 even though nothing happened other than the program started scanning and it sees a false to true transition because that rung was false and then went true. In other words, it went from program to run. So we'll get in here and we'll do these instructions, and I'm talking about add, subtract, multiply, and divide, just basic math instructions, not the more advanced ones. And then later on, maybe in one of the later volumes or semesters or classes, maybe we'll do some of the more complex or convoluted mathematical operations. So let's get at our math. We have really one rung of interest here. That's the third rung, and that's the rung that has the add and the subtract function or function blocks. The first 2 rungs simply give us the ability to increment or decrement values. So we have 2 values there, count up down 1 and count up down 2. We can count either number, and then of course input 1 and input 3 are the count down. So we can count up 2 different numbers and use them for add and subtract. So when you look at the third rung, the thing you need to understand about math instructions, they are not an output type instruction, meaning we can put 2 of them in series. So we have an add and a subtract in series. We don't have to put them on separate rung levels. And notice that there's EN and ENO. So enable and enable output. Whereas the counter instructions have CU for count up and then QU and QD. So those are outputs based on the state of the instruction or the data type. Looking at the add instruction first down there, if I take and let me bring over the simulator, we're going to need that. And I guess we'll just leave it here simply because we're not blocking anything that you need to see. So if you keep your eye down here, 0 plus 0 equals 0. 0 minus 0 equals 0. So we'll throw in a value of 1. 0 plus 1 equals 1. 0 minus 1 equals minus. So you can have negative numbers. If I keep going in that direction, it keeps going negative, the subtract. Or if I go in the positive direction, two plus 0 is 2, 2 minus 0 is 2. We go back up here. Now I'm toggling input 0. So I'm counting up this number. Now I'm actually counting up both numbers. I'm not counting down. To count down, if I clicked on input 1 here, you see for the top counter that went down, one more click, it's down to 0. Now notice that once I get down to 0, it's not going to go any lower. It won't go down to -1. If I wanted to count down the second counter there, that's input 3. Now I'm back to 0. Now I don't have a reset function. Probably the simplest thing to do is just to go in and create a variable, a Boolean type variable called reset, and then throw that variable in here and toggle it right from your mouse. I can't think of anything else to say about add and subtract. Really, these labs are just about you exercising the instructions, and you'll get them instantly. There's nothing complex about the math instructions. But remember, math instructions aren't true or false. They either are executing or they're not executing. So the rung state in is important, but they are not instructions that directly turn outputs on and off. However, the output for any of these math instructions could be something that eventually ends up as an actual hardware output. Let me just, for grins, I'm trying to make this interesting or more interesting. I'm going to pause, change some logic, and come back. Okay, let's give this a whirl. First, let's look in the buffered outputs. What I did was I created a double integer called em_outputs, and I have 0, 0.1, 0.2, 0.3 in parallel with output 0, 1, 2, and 3. So either one of these can turn on this bit. Now output 0 is on right now because we left it on. In a previous lab project, we left it on. In other words, we told it to turn on and never told it to turn off. Okay, so now it's off. In other words, there was no logic turning on this bit. That bit was left on because the last time that this simulator ran, it had a program in it that turned on OUT00. I downloaded a new program, so the logic never scanned and turned off output 0. It's off now. So now what I want to do is go back to comparison, and then I want to increment so we have a value of 1. So we have 1 in embedded outputs. You see down here 0 is on. If I do another one, now you see we have 2. Now, if logic stands to reason that, and we're talking down here, ignore rung 3, we're talking about rung 4. So we're adding the CV, control variable, from both of those count up down counters, and we're putting the result, the sum, in a double integer called embedded outputs. And I have the first 4 bits of this double integer controlling output 0, 1, 2, and 3, the actual hardware outputs. So if I increment one more time, this should go to 3. So you would expect both of these outputs to be on. They're both on. If I go one more, that would be 4. So you're going to see 0 and 1 turn off and 2 turn on down here. And if I keep going, now 5, 6, all 3 on, 7. and that's as far as it goes because that's what I've got. In other words, I can't count up any higher than 7. So even though I'm toggling this, it's going nowhere. Now I could always, no, I can't do that. I can't even go change this to 7 because this rung is true, and it will add these two values and put it in embedded outputs whether I like it or not. So that's as far as I can go. If I put in a higher value for process variable, then I could keep counting up. And because I have 4, then if we got up to 15 in our count, then all 4 of these would be on. If we go to 16, then this one would go on, and these would all be off. And of course, we only have the first 4 bits, 1s, 2s, 4s, and 8s of our binary. Okay, that's everything I can think of to do with add. And this, by the way, was a lot easier with RS Logics and those controller platforms because you could move an integer, single integer, double integer, right directly to the entire I/O module defined data type to the word for all the outputs. You can't do that here. This is one of the few methods that you can use to do this. If you want to actually take a word like embedded outputs, now that's a Boolean, but it's part of a double integer embedded outputs. You would have to put this in parallel with your buffering. Now, if you didn't have buffering, then you would have to put this in parallel with the logic that turned this bit on and off wherever it's at in your logic. Very complex. Previously, I described to you that I typically use add and subtract to increment and decrement numbers. And you can see down the bottom rung, last rung, I am adding the count to the embedded outputs, and then I'm storing it in embedded outputs. So if I run this right now, 0 plus 0 is 0. Nothing's going to move. Now, going back up here to the counter instruction, whenever I execute this, now as I turn on input 0, on the false to true transition, this will increment once. So this type of instruction executes once for each false to true transition. Go back to false. I'm going to leave it at 1 because that's what I need down below. But notice this stayed on for a couple seconds and nothing happened. Now down here we're going to take the count, and I say I used the wrong one, so let me do 2 here. I needed a 1 because that's what I used down here. I use count up down 1, not 2. So now we see we have 1. We're going to 1 plus 0 is 1, and it's going to store it in the same variable. So the same variable is used twice here. So I'm incrementing that variable. But watch what happens as fast as I can turn it on and off. As fast as I could click it, it incremented to 291. So that means 291 program scans passed between when I clicked 9 on and when I turn it off. So I'm going to double click it really fast. I'm not going to wait for it to turn on and that I can see it light up, just bang bang. Okay. Well, now we went up to 465. That's because I didn't zero it. So to zero it, you can do this with almost any variable. Variable, right click, variable monitoring. And when the value comes up, and I wish it came up completely in view so you didn't have to scroll. So I'm going to send that back to 0. And you can see now it's back to 0. So let me do that again as fast as I can do it. That's as fast as I could click it. And it was 119 program scans. Of course, you could always take me on, see if you can do it faster. And I might be able to do it faster. That's not the point. The point is, if you turn on a math instruction, it is going to execute every single program scan. So before this one, the reason that this number doesn't start zooming up as a scan counter is because when it executes, it's adding these two values, and it executes this thousands of times a second. But the answer, it's always the same. This is 1 plus 119. So on the very first scan that this goes true, that's going to go to 120. The next scan, 121, 122, and so forth. And the subtract works the same way. It will decrement by whatever value you have. In this case, I'm using 1. So if you replace this with a minus instruction, then you would be subtracting 1 every program scan. Now let's say, like me, I like using the add and the subtract and have it work against the same number. In other words, I increment, we'll call it, variable 1 by 1, and I decrement it by 1 using the add and subtract instructions. But if I want to count events, false to true transitions, then I'm going to have to do something in front of these instructions to prevent them from being scan counters. Let's do that. Okay, here you see we've added a rising edge trigger between input 9 and the add instruction. Now keep in mind that the add instruction is going to add input 1 and input 2 on every true program scan. In other words, if the enable in is true, it's false right now, but if it were true, it's going to add the value of input 1, it's going to add it to input 2, and store it in output 1. Now in this case, we're wanting to increment a value using the add block instead of using a counter. Instead of counting up, we want to add up by 1 every execution. So notice that input 2, EM outputs, and output 1 is EM outputs. So we're adding 1 to input 2 and then storing it at input 2. Now it says output 1, but notice that the variable names are the same. So this is how you would use an add block to increment. Now we don't have to increment by 1. It could be any integer value or double integer that you want to put in input 1. But in this case, we're treating this as a counter, and we want to count false to true transitions just like a count up instruction would. What I like about the rising edge trigger instruction is that it's pretty straightforward and simple. You don't actually have to name it. Now this one's called R underscore trigger underscore 1. If I add another one, it's going to be underscore 2, underscore 3, and so forth. But I could actually name it. But it's easier just to throw one of these in there. Now, if you watch, I'm going to turn on input 9. You notice it goes true, but you don't see the output Q from the rising edge trigger necessarily changing state. But you do see that EM embedded underscore outputs is now 1. But we're still executing. We're still running thousands of scans per second, but you see the value only incremented once on the rising edge from input 9. Turn input 9 off, turn it back on again, it increments to 2. Turn it off. What you don't see is any change in the state of the output of the rising edge trigger. Now just for grins, we have 2 more instructions here that we're doing, and that's what we call it in the manual, just for grins. And if you look at this, you get the gist of what we're doing. We have a rising edge trigger and a falling edge trigger. Now remember, the lab projects like this, we're demonstrating how the instruction works. This is not a practical application. So you could maybe use this little piece of logic here, rung 5, for something. But really the only thing that it suffices for is to demonstrate the difference between a rising edge trigger and a falling edge trigger. And notice again that we're using the count up value for count up down counter 1, which is 1. It could be 2, could be any number. And we're storing it in running. So we're adding 1 to running and storing it in running. So we're incrementing. The one down below we're also incrementing, and that happens to be from count up down instruction 2. In this case they're both 1. So we're just in both cases adding 1 to the value running or adding 1 to the value running 2. So when you look at this, you would say, okay, when input 5 goes on, I'm expecting the first half of this to increment. And you see it does. Running is now 1. When I turn it off, this is the falling edge trigger, I would expect running to stay at 1 and running 2 to go to 1. Straightforward and simple. We did ask you in the manual, if you were to change input 5 from a true if on to a true if off, how would that affect the variables running and running 2? Well, remember that it's based on a false true state in to the clock input on these triggers. The rising edge trigger and the falling edge trigger, it doesn't have any idea what's off to the left. There could be anything out there. All it knows is that the rising edge trigger instruction goes true for one program scan when whatever's coming into it goes from false to true. And the falling edge trigger, when whatever's coming into the clock input goes from true to false, it's on for one program scan. Whatever you have out there in place of input 5, true if on, true if off, it really doesn't matter. The trigger instructions are not dependent on whatever's off to the left. Okay, we've added our next rung of logic, multiplication and division. And I didn't delete the previous rungs. I instructed you to do so. It's up to you, as long as you're not reusing the variables. Now, I'm not talking about count up, down, 1 and 2 CVs. Those are just values from the counters on the first rung. So the first question was, is there any interaction between these two operations? Absolutely not. Notice that the color of the rung is red all the way across. That's because these aren't like count up, count down instructions that have an output based on a comparison of a process variable and a control variable. So the ENO is enable out. In other words, the enable in goes straight through the enable out to the next instruction. And this is a benefit. And you can alter that on some of these instructions. But for now, let's leave that alone. So the first instruction, I'm multiplying 0 times 0, the result is 0. In the second instruction, I'm dividing 0 by 0, and the result is 0. You'll never get in trouble with multiplication, not unless you accidentally drive an overflow. In other words, if you're using double integers, there is a maximum value. So if you take and multiply the maximum value of a double integer times the maximum value of a double integer, the result is going to be larger than a double integer. Now there's where you could get in trouble with an overflow. With division, anytime you divide something by 0, theoretically the result is infinite. So again, in this case, we're dividing 0 by 0, so we're not in any kind of trouble. And I ask you, are there any interactions between these two instructions? No, there's not. Now they're both using the same values for input 1 and 2, but they have a different variable for the output. So the output of 1 is not used in consideration with the other. So there's no interaction. Does it matter which is the first in the rung? Does not make any difference. It would still be the same. Would the results be different if they were each in their own rung? No. They're somewhat autonomous. In other words, one's not dependent on the other, especially since rung 6 is unconditionally true. You could stack up a dozen of these math type instructions in series, and they're all going to execute fine regardless of the results of any one individual instruction. Okay, looking at the red-blue indicators, what conclusions can you make about these two instructions? Well, they both have a true in. That's all you can make. Increment, count up, down, counter 1 to 1. And then I asked, does it increment? So I'm going to go up here. That would be count up, down, or counter 1 is input 2. So I'll turn on input 2. And I see that I did fault dividing by 0. I thought I was going to get away with dividing 0 by 0, and I didn't. So I didn't see anything in my logic that told me there was a fault. But now that I'm looking around and paying attention, I see that I have a fault up here. Okay, so we're going to go look at that fault. Okay, so if I go to the right place, you know, basically I disconnected the CCW from the simulator, and it says I have a data overflow. And that data overflow is caused because I divided by 0. As long as we're still connected, then I can go to diagnose. You have to click on the micro 8 whatever you got tab. In this case it's an 850. Click on diagnose, fault, and it comes up and gives you the fault location and says data overflow occurred. So you see those really the same piece of information, data overflow occurred. So it's the same fault number, 0xF860. Now there's a couple ways that you could undo this fault. Probably the simplest is to stop the simulator and then download again, because it's the simulator that's faulted, not your program in CCW. CCW doesn't fault, but the simulator does. So we're going to start the simulator back up and see what kind of messages we get to see if you have to do anything additional to get back running again. Okay, so we're connected again to the simulator, but the simulator is still faulted. So if we go to the Micro 850 tab and go to diagnose, go to fault, we could clear the fault. Now we had more than one fault in my going back and forth. I created the fault a second time, but you see it's the same fault code. So if I clear the fault here, I'm clearing the fault in the controller, the simulator. Okay, you see it's no longer faulted, but it's no longer running either. And then I can go back to run, and of course if I haven't fixed the problem, it turns right around and faults again. I'm going to put it in the program mode and then clear the fault. Then I'm going to go to the logic. Remember, it said it was in the comparison program, and we can't be dividing by 0. Count up, down 2 has to have something in it. So I'm going to increment We'll put it in run. Nope, it's going to fault again. Okay, I've went and directly changed the CV for count up down 2 to 1. So I'm no longer dividing by 0 when I go into the run mode. So I'm going to go back to the run mode. And you see now it's running and it's not faulted. Now I'm going to go check my affinity, Control Alt Delete, Task Manager, right click, set affinity. Okay, I'm still set to a couple CPUs, so I'm good. If that goes back to all the CPUs selected, then we tend to get a watchdog timer fault. Okay, so now here we are with our multiply and divide, and we're not faulting. Now, hopefully none of this confused you, but you can't divide by 0. Not on pencil and paper, and especially not in a computer. I did talk about the data overflow in the manual, that for a double integer has a range of minus 2147483648 minus value to a plus 2147483647. And the reason this overflowed happened is because you can multiply by 0, but you can't divide by 0. If we cleared the fault, would that correct the problem or just the fault? That would clear the fault, but it wouldn't correct the problem. So in order to correct the problem, we have to eliminate the possibility of dividing by 0. Now in this case, I just went into the database and changed the controlled variable for count up down 2 to 1, and then put it back in the run mode, and that's what you see right now. And one thing I did to prevent dividing by 0 is added a greater than instruction in between these two. So I'm going to pause, do that, and come back. And there you see I've added in a greater than instruction. So this value here has to be greater than 0. Now we're talking whole numbers, so that would include 1. So 1 would be legitimate. But you can see that this instruction has an output that can be true or false, whereas the math instructions do not. So if I were to count up down 2, you see it's 0 right now, and that would be input 0. So go up here and toggle on input 0 and back off. Now we can see that 1 is greater than 0, so we have a true out. And typically when I write programs where I'm using math instructions, especially the division instruction, if I think there's any remote possibility of dividing by 0, I will take whatever the variable is in input 2 of the division instruction, and I will use it in a preceding greater than instruction that says if it's not greater than 0, then the rung is false and the division doesn't execute. These are just a few little things to look out for when you're using the math instructions. If I don't explain where to get the manuals and what they are in the videos, then I get dozens of emails asking where to get the manuals. This RS Logix 500 manual is really the culmination of quite a few years of MicroStarter Lite, MicroStarter, and RS Logix 500.
RSLogix 500 will program all SLC 500s and all MicroLogix. MicroStarter and MicroStarter Lite will only program MicroLogix. The Starter is not free. It's about $200. Starter Lite is free, but Starter Lite will only program the MicroLogix 1000 and 1100. Then for 5000, RSLogix 5000, Studio 5000, we have 3 volumes, Fundamental Programming, Programming Examples, which is really one manual broken into 2 volumes, and then the Advanced Discussions and Lab Projects. The software for this hardware that this programs, the least expensive license is about $1,000, just under $1,000. And the hardware is also relatively expensive. You can find used compact Logix with some I/O for in the $500 range, but the minimum license is going to be just under $1,000. For Connected Components Workbench with the Micro 800, the software is free. So you don't have to buy any hardware. Starting with version 12 of CCW, they included a simulator that works really well. And we really emphasize the simulator in all of our manuals. We also have a separate volume for PanelView 800 and PowerFlex 525. The PanelView 800 projects in this 3rd volume, they are integrated into the actual lab projects in Part 1 and Part 2. So after you do a lab project in Part 1 or Part 2, for the most part, most of the labs, you can then immediately go to the 3rd volume and do a panel view lab that integrates with the project you did in Part 1 and or Part 2. Not all the projects in Part 1 and 2 have PanelView 800 projects that complement them. And then for PowerFlex 525, we have both projects using controllers, and also we show you how to hardwire your PowerFlex 525s with push buttons and lights. For the volumes that you see, the lecture discussions are complete and available for all but the Part 2 of the CCW manual. Most of them are complete and currently going on YouTube free, and we don't have any done yet for the 3rd volume for the PanelView 800 or PowerFlex 525. But keep in mind, you don't need to subscribe to the videos to do the projects in these manuals. The videos are for people that would like a little bit more explanation and tutoring. Have a nice day.